Okay, this is a video recording of my independent study presentation. My name is Ryan Polacheri, and I am a Master's of Computer Science student here at the University of Iowa. And for the past 2 semesters, I've been working on this project titled Real-Time Carbon Footprints and Energy System Modeling at the University of Iowa. And I've been working with the Departments of Civil and Environmental Engineering at the university, as well as with the university's energy services company, ENGIE. And so when we started this project 2 semesters ago, we wanted to build another way to visualize the energy resource usage of our campus buildings. So here's a picture of our campus, and of course these buildings on campus use a tremendous amount of energy. And what we wanted to do is visualize that energy in terms of a carbon footprint so that we could see in real time what is the carbon impact of these buildings on campus. And so that's exactly what we did. We built this dashboard that allows you to select a building and select a time frame and see the carbon footprint of that building at that time. And so we can see for Siemens Center, the carbon impact from 2 to 3 p.m. on December 9th was 487 kilograms of CO2. And then, of course, we break this down by specific energy resource usage, so 155 kilograms from electric, 327 kilograms from steam, and 4 kilograms from chilled water. So, yeah, not a lot of use for chilled water in the middle of winter. But so this is the dashboard we built, and the idea being that it was a good way to engage the community on sustainability. So we could do things like display this dashboard in real time at these buildings, just to raise awareness on the carbon impact of our facilities. So a little bit more detail about how this calculation is done is first, we look at a building. So in this case, this is McLean Hall. And we take a look at its usage, and we have usage data in real time. We have all sorts of data in real time. And we can see how much electric, steam, and chilled water it is using. And to figure out its carbon impact of that usage, we have to backtrack. So this steam came ultimately from our power plant along the river, and this power plant might have burned coal or natural gas, or some of these energy pellets, which we'll talk about later, or some of these oat hulls, which we'll also talk about later. And depending on how much of each of those resources that this power plant burned, is going to impact our emissions that are associated with steam. If we're burning all biomass, then carbon impact is very low. If we're burning all coal, carbon impact is very high, for example. And so that's steam and electric. So most of our electric comes from our utility company, which tends to be very, very good at providing clean energy most times out of the year. So Mid-American Energy Company, most times of the year we can assume that our energy is low impact wind energy. But it could be coal or natural gas, depending on the time. But we also have some electric that we generate on campus ourselves. So we have this co-generated electric. Co-generated electric is steam that we take out from the power plant, divert it to these turbines, and these turbines produce electric for us. So to figure out the carbon impact of this electric coming from here, we first have to, of course, calculate the carbon impact of our steam. And there's some natural gas engines and some solar arrays on campus as well. And depending on the mixture of how much of each of these energy sources are being used, that will impact our carbon footprint of our electric usage. And then chilled water. Chilled water is a product of of electricity and of steam on campus. So once we have those calculated, we can look at the amount of those resources that are going into these chilled water facilities, and we can see how much chilled water is coming out, and then we can determine the carbon impact of that energy resource. And once you do all that, then you can see how much emissions that a given building, in this case McLean Hall, is responsible for out of the total emissions of the power plant. Okay, so to express this more numerically, these are the metrics we're looking at. So our first one for electric is kilograms of CO2 per kilowatt hour of electric. And we can, of course, graph this over time. So this is an 8-day time span where we render this metric every hour. And for a kilowatt hour, on the low end, the cost is 0.3 kilograms of CO2 per kilowatt hour. On the high end, it looks just above 0.6 kilograms of CO2 per kilowatt hour. For steam, we want to measure kilograms of CO2 per MMBTU of steam. And now an MMBTU is a much bigger unit of energy than a kilowatt hour. So we'll see that this metric fluctuates from around 55 kilograms of CO2 up to looks like 75 kilograms of CO2 per MMBTU of steam. And then chilled water. Chilled water is kilograms of CO2 per gallon of chilled water. So obviously a very small unit of energy. So our metric is much smaller here. So 0.002 kilograms of CO2 per gallon of chilled water is where we're hovering around. And these metrics, they change both by the minute or by the hour over the course of a day, but also throughout the course of a year. Okay, so we can use those metrics to build these nice dashboards to engage the community on sustainability, but there's also some other things we can do with them. So we can do carbon-based load shifting. So load shifting is something that big manufacturing companies probably already do in coordination with their utility company. So if you have a manufacturing operation, they probably ask their utility, when is the best time we can run our manufacturing operation to lower our cost for electric or natural gas or something. So they load shift, they run their process when the price of energy is cheaper. So we do cost-based load shifting. But now that we have these metrics, we can do carbon-based load shifting and do the same thing where we can optimize manufacturing or computational processes based on our carbon metrics. But on a more campus-oriented level, you could load shift, for example, vehicle charging. As long as the vehicles are charged by the end of the day, it doesn't matter when you charge them, but when you charge them could impact the emissions resulting from the energy use to charge them. Heating and cooling is also technically possible, where if a building needs to cool, but there's some flexibility, maybe it can wait 30 minutes to cool, then perhaps, if you have a lot of solar on campus, maybe right now it's cloudy, but 30 minutes from now it'll be sunny, and maybe weather models can predict that. And if you cool the building 30 minutes later, you might save on your carbon impact. And so these two papers here are kind of where I got the idea from. So they talk about doing this in the context of cloud computing and also in the context of battery storage. So I recommend those papers if anyone's interested in this carbon-based load shifting. Okay, so let's see a numerical example of this load shifting, just to see kind of how the numbers play out. So imagine we have a process that requires 20 MMBTUs of steam, 5 megawatt hours, and 5,000 gallons of chilled water. And these numbers are completely arbitrary, but it'll give you an idea of how our carbon impact changes based on when we use these resources. So the best time to use these resources in terms of your carbon impact is right here. So that will yield 2.67 metric tons of CO2 if you use those resources then. If you use these resources here, though, it's going to yield 4.26 metric tons of CO2. So the savings is 1.59 metric tons of CO2, which is significant. So if you're not familiar with the unit of a metric ton of CO2, you can think about it like this. To get 1 metric ton of CO2 back out of the atmosphere will require 1 acre of US forests working for a year to pull that carbon back out of the atmosphere. So loosely, you can approximate in that way. 1 metric ton is 1 acre of US forests working for a year to offset that 1 metric ton. Okay, so we see the metrics that we're after, and we see some uses for them with these dashboards and with this carbon-based load shifting. But these metrics were not easy to produce, and we ran into a lot of challenges. So in terms of the data we need, our current model is using 98 data streams to calculate these numbers, and most of those data streams come from the University of Iowa's Energy Systems Digital Twin, which is just a digital representation of our energy system. And a couple data streams also come from EIA.gov, so we can get electric grid-related information. So there's a lot of data streams, and we have use cases to add even more data streams, but our current model is at 98. And some of these data streams have very complex relationships. So on the simple end, if you want to calculate the amount of carbon associated with burning natural gas, well, that's a simple calculation. You look at a data stream that tells you your flow of natural gas, and you multiply that by an emissions factor, and you have your carbon impact of that natural gas. So that's on the simple end. On the complex end, for example, when you need to determine how much steam from our operation is getting routed to those steam turbines, our co-generated electric, that's a much harder calculation requiring around 12 data streams. And the formula with how those data streams are related is quite complex. And then, of course, just another general problem of working with all these different data streams is there's 14 different units between these 98 data streams. So MMBTUs, pounds, kilowatts, megawatts, gallons per minute, megawatt hours, right? So there's all these different units. Here's my favorite one, the empty string, right? We have a few data streams that don't have a unit recorded on them, so we have to kind of backtrack and figure out what the unit is. So a lot of unit conversion going on, and also if you look at the rates of these units, that also creates complications. So MMBTUs are measured over an hour, but gallons per minute is over a minute, and megawatts is megajoules per second. So the rate of these units is all reported slightly differently, and that's, of course, going to also create some issues when we want to make a real-time carbon footprint. Okay, and just kind of to show the complexity visually, this is one steam boiler at our power plant. This is boiler 10. It burns natural gas, and it burns those energy pellets that we'll talk about. And this is the digital twin representation of this boiler that's kind of expressing all the key functionality of it. And from the perspective of the operations team and the engineers that maintain this boiler, all this data is important to them, and they have alarms set up so that if values are out of line, alarms will go off. They'll get contacted and they can investigate the issue. But for the sake of modeling carbon emissions, we only care about a few pieces of this data. We only care about energy pellets going in, natural gas going in, and the amount of steam coming out. So from here, we only need, from boiler 10, we only need three data streams out of, I don't know, maybe 100 that are here total. Okay, so now we're going to introduce, so that's the digital twin layer. We're going to introduce the modeling layer. So here's another view of a boiler. This is the model view of boiler 11. So boiler 11 takes in oat hulls and energy pellets, and it also takes in coal. So these are its inputs, and we want to execute some functions across this data. And out of this boiler comes steam, but also the CO2 impact of that steam. And we also want to track the fuel cost of that steam. How much did this steam cost to generate? So this is a much better view, much simpler to look at and to use for modeling than the big complex digital twin. And of course, this is just one boiler in our energy system, and we can design and build these various nodes that take in their data and compute what they need to compute and organize them in a network. So here is a loose network of our current model of the University of Iowa energy system. So on the left end here we have some boilers and 5 power plant boilers, 2 other boilers. We have grid resources. We have co-generated electric. We have chilled water. Mostly everything is in this network here. And at the end of the day, you start on the left end where we're first creating the resources, and those resources travel through the network. And then at the end, we have the three resources that we provide to consumers: electric, steam, and chilled water, all over their carbon impact and the cost, the monetary cost it took to generate that resource. Okay, so building these little nodes in a network that take in this data and run these functions, we need some help to do that. So we built custom software to allow us to design these models of energy systems, and that software is written in C# using .NET 7. The code for it is all available on GitHub. And more broadly, our software system includes this desktop application, Unified Data Explorer. We'll see this and demo this visually. This is what you'll see. And Unified Data Explorer is used to both find the data streams you need and then build a model of your energy system. So that's the tool we use on that end. But the system more broadly also has a web API, which you can use to programmatically get these emission factors. And it has an experimentation app, which we won't look at the experimentation app, but we'll see results when we show our experimental results. Those came from this tool here. And then on the back end, there's also a SQL Server database to store our models, our energy system models, as well as our experimental results. Okay, so with that, let's take a quick look at the software. So here's the entry point of Unified Data Explorer, and the first thing you can do is, of course, explore. So it takes a lot of work to find the 98 plus data streams that you need. So here's a search window where you can go in here and search and get the data you need. And that's kind of like an open search if you know what you're looking for. But there's also some of our data streams are organized in a hierarchy. So in that case, you can navigate the hierarchy through this app. And for example, look at McLean Hall here. And so these are the data streams that are associated with McLean Hall. And for example, we can render the electric demand of McLean Hall. All right, so we can use this system to navigate the data we need. You can also navigate EIA data from here. But then the most important part is, you found these data streams, and now you want to go and build your model. And so you don't want to have to find them again. So you can. There's also a hierarchy structure here, where you can save off the sets you found. So for example, if you're modeling boiler 10, you can open your set of data streams that you've saved for boiler 10, and so that you have them ready when you're going to build your model. Okay, so the other thing, so now you found your data and you want to build your model. So let's see what that looks like. So we have several models for University of Iowa. I'm going to open this one here, and each of these items on the left is one of those nodes in that network. So a simple node is, for example, boiler 7. Boiler 7 is categorized as an exchange node in that it has a product, and in exchange for that product, it also has costs. So our boilers are represented with exchange nodes, and this is on the way simple end of the modeling process. So, for example, we have this function here that tells us, given a data point from our stream of raw data, how do we convert that to a unit of energy? So that's what this function is doing. That's what it's for, is get from raw data, how do we get to this abstract notion of steam? And so that tells us how to do that here, tells the system how to do that here. And then on the cost end, for CO2, we want to take in a data stream. In the case of this boiler, it's just a stream of natural gas flow. And we tell the function, well, given a stream of natural gas flow, how do you calculate emissions from that? And there's helper functions and such built into this system, but we tell it how to do that right here. And for fuel cost, so the fuel cost for natural gas, it actually isn't too well done in the model right now. So we take in a natural gas flow and we just multiply it by a constant. But what would be better to do is take in two data streams, both our natural gas flow and the market prices for natural gas, because obviously the price of natural gas fluctuates. So we should really be taking in those two data streams and multiplying one by the other to get the fuel cost of this natural gas. But I didn't have time to add that before this recording. Okay, so that's on the simple end. On the more complicated end, we have a node that represents how much steam is going to our electric turbines for co-generated electric, and so this is categorized as a splitter node here, right? Because it performs a split of how much steam diverts in this direction, and so this takes in 12 or so data streams here takes in 12 or so raw data streams, and the function that relates all these data streams and eventually tells us our answer for how much steam is going to our co-generated electric is all represented in this function. So the idea is no matter how complex your data is, however complex the relationship between data streams are, you have the full power of the C# programming language to to use to calculate what you need to calculate. So, and of course, this is strongly typed here. This function is strongly typed. So, I mean, you have to return a unit of energy because that's what we're expecting at this point in the process. So, also strong typing is a huge plus here to help you build your models correctly. Okay, so this is what the designer looks like here. We got all sorts of nodes that do various things, and what we can do now is execute our model. So we pick a start time and an end time, and within that start and end time, we can render our data at any resolution, really. So we can render it every second, which is really overkill, but we can do it. Every minute, every hour, every day, and so forth. We could do more, but these are the 4 options we have now. So I'll render it hourly for yesterday. And it'll take a second to run. There's a lot that has to go on behind the scenes, so we'll give this a second. But another thing to note is a reason for building the software in this way, right, is we didn't want to just build an energy system network for University of Iowa. We wanted to build a tool that could be used to model any energy system anywhere. So, of course, I have folders here for all the ENGIE partnering institutions. So if they want energy models for their energy systems, they could use this tool to build it. So, okay, so our model's executed, and from here we can investigate what our data looks like at every node in the network. So if we look at boiler 10, we can see, by hour, this is how much steam measured in MMBTUs that boiler 10 produced, and this is the money that it cost us to produce this steam, and this is the amount of CO2 that is associated with this steam. And so that's just a view at the beginning of the process, but if we want to look later in the network, we sure can. So, for example, co-generated electric, we can see that our electric turbines from the hour of, 7 to 8 a.m. produce 24,000 megajoules of electricity. And this is how much money it costed us, and this is the emissions associated with this electric. Okay. And so that's a view of the software and what it does for us. What we'll look at now is some experimental results that we can produce from this software. But before we do that, we want to do an accuracy test, right? So it's very easy to build buggy software, and it's possible that there's issues and we're calculating things incorrectly. So we wanted to compare the numbers our software produces against ENGIE's validated data, or ENGIE's validated numbers that they report to the EPA. So this is ENGIE's 2021 power plant CO2 emissions that are used for EPA reporting, and their number for 2021 was 195,851 metric tons of CO2 worth of power plant emissions for the year 2021. So this is the number we want to try to match with our system. And we get close. Our system produces 184,480 metric tons of CO2, so about 5.8% error. But the good news about our system is that the difference in resolution. So the resolution for this number is once per year. ENGIE produces these numbers, and our system can produce this at any resolution. But in the case of this graph, it produces this number once a day for the year of 2021. So we can see how our CO2 emissions rise and fall throughout the year. So at the peaks of these emissions graph, there's probably high demand for energy, and we're probably using coal to meet that demand, and that is going to lead to a higher CO2 emissions for that day. On the low end, we're probably not burning coal. And in fact, I know that is what's happening on the lower end. Not only are we not burning coal, we're also burning biomass on top of that. So our emissions are much lower at these low points. Okay, so now that we have an idea of the accuracy of our system, we can run experiments with it. So the great news about setting up this piece of software, building this piece of software that with these models that can model your energy system is now you can plug and play these different nodes in the network to see how changes of the energy system impact your emissions or your fuel costs at the end of the day. So for example, if this node's a boiler, we can ask the question, well, what if this boiler didn't burn coal? What if it burned energy pellets instead? Or what if the university built a solar farm on campus or rooftop solar on campus, right? And we add this node to our network, how does that impact our emissions at the end of the day? So it's a great vehicle for experimentation because it's so easy to change these nodes out and see the effects on the broader system. So the first experiment we did is of course related to the university's no coal by 2025. So the current I think the current plan for getting off of coal is to replace all the coal we're burning with these energy pellets. So these energy pellets are from a company called Convergyn up in Milwaukee, and they're mostly biomass. And that biomass could be grasses, it could be papers or cardboards from industrial waste. So various different kinds of biomass is in these pellets, and so they're mostly biomass, but then they're also pre-consumer plastics. So plastics that would be waste of manufacturing processes, but instead of that plastic going to the landfill, it gets packed into these energy pellets and used as fuel. And so on the surface, if we just look at these numerically, coal is 1 kilogram of CO2 per pound burned, and these energy pellets are 0.6 kilograms of CO2 per pound burned. So lower carbon impact per pound, but the BTUs per pound, this is the amount of energy that's in a pound of these substances, is lower. So that means we're going to need to burn more energy pellets to make up the difference in energy content between these pellets and coal. And these energy pellets are also more expensive than coal. So that is something we should also take into account. Okay, so we run this experiment. We say, what if we made up all the energy content we get from coal with these energy pellets? So we can see this red curve is our emissions for the past year with coal, and our emissions replacing coal with energy pellets is this blue curve. So you can see on the low end here, right? So we're not burning coal at this time, so there's no emissions saved. But you can see at the peaks, when we're burning coal to meet demand, for example, or we're burning coal because we ran out of money in the budget, or for whatever reason we're burning coal, if we use energy pellets again, we can shave these peaks off and have an impact on our system's carbon emissions. And so if you add up the difference in these curves over the year, you have 18,220 metric tons of CO2 prevented from this change in fuels. And again, the metric or the comparison I'll use is that's 18,000 acres of U.S. forest working for a year in order to pull this carbon back out. So this is a real impact on the environment. But of course, these energy pellets cost more, so we also want to know how much more is this going to cost us. It's great that it saves emissions, but we should also know kind of the monetary impact of doing this change. And so the difference in these curves is pretty small, but if you added up the difference over the year, it's about $827,000 more that we would pay in fuel. So this transition isn't free. So what we saw is that this change in fuel saves us 18,000 metric tons of CO2, but costs us maybe $1 million more. What's another lens we can look at this through? I mean, of course, carbon CO2 emissions do have a monetary impact. It's just in today's age, the people who emit these CO2 emissions don't have to pay for that impact, at least not directly. So, of course, you emit CO2 and it ends up in the atmosphere and contributes to climate change, and now natural disasters are going to be more severe, which is going to cost more monetary damage when they strike, and rising temperatures and droughts could raise the price of food costs. So, I mean, there is monetary impact to emitting this carbon. We just don't have to pay it. So this study here estimated that impact to be $185 per metric ton of CO2 emissions. That's what they determined to be the social cost of carbon. And now that's great, but that's great that the research investigated and came up with this number, but that doesn't necessarily mean society is going to agree to pay that. So this number is closer to what the U.S. Government might pay someday. So the current U.S. administration prices CO2 at $51 per metric ton. So they don't actually pay you these $51 if you were to save on emissions, but this is the number they're putting on it. So it's probably closer to what we would see if there was a carbon market in the United States. And so establishing this carbon market where organizations were compensated for saving emissions at this rate of $51 per metric ton. If it was enacted, of course, we would actually gain money, right? So 18,000 times 51 minus the amount more we spent in fuel. So it's about $100,000 of income we would get. So I mean, even if you don't care about the carbon emissions impact, it's a great reason to lobby for a carbon market, because this would actually be income for the university. Okay, so let's keep going down this path. Let's see if we can use an even less carbon-intensive fuel to replace coal, and kind of see how that plays out. So this fuel on the right is oat hulls, and oat hulls are a byproduct of oat milling, and I believe the university used to get them for free from Quaker Oats. Right? So Quaker Oats would have these as a waste, and they would have to pay to put them in a landfill. But what they worked out instead was sending them to the power plant at the university, and we burn them for energy. So they used to be free, but now biomass is growing in popularity, and so we pay this much per pound for them. So they're cheaper than coal, actually. But their energy content here, 7,000 BTUs, is much lower than coal. And kilograms of CO2 per pound burn is reasonably, you could call zero, because when these oats grew, they pulled carbon out of the atmosphere, and you burn them, it puts the carbon they took out back in. So we could say there's zero. And if we run this experiment, replacing coal with these oat holes, obviously the savings is going to be tremendous because of that big zero for carbon emissions. So savings is tremendous, of course, except when we're not burning coal at these points in the curve. But otherwise, if you add it all up, it's 57,000 metric tons of CO2 prevented. A huge impact there. And we want to know how much is it going to cost to do this. It'll actually cost less to do this than it will energy pellets. So $300,000 more in fuel costs because this fuel is so much cheaper than coal. Now, so the numbers play out for these fuels, I think. I mean, oat holes, for example, 57,000 metric tons of CO2 saved for only $300,000 more in fuel. So that plays out numerically, but I should say that there might be physical limitations to making these changes in fuel. So the engineers that manage the power plant might say, we can't run a boiler off of oat holes because they burn too quickly. They don't have a sustained burn of their energy content, or they cause hot spots in the boiler, which causes damages. So there could be physical limitations to all this data, or to all these experiments, but we're kind of ignoring that for our modeling. Okay, and to sum up, if we want to kind of push these experiments back down on a more local level, we can see the impact of these changes on a building's emissions. So it's the same emissions from the second slide. Siemens Center, 487 kilograms, and these are the savings for Siemens Center if we make these changes. So just wanted to show this to show that if academic departments or buildings are concerned about their carbon footprint, I mean, they can be supporters of these changes at our power plant as well, and that will help their impact. Okay, and that's it. I just wanted to give a special thanks to George Patterson and Melissa Gilmartin from ENGIE. They helped tremendously with this project. It would not have been possible without them. There's no way I would have figured out all I needed to figure out. So great thanks to them, and of course to Jerry Schnoor for exposing me to this area of research through his classes, and for being my independent study advisor for this project, and of course the University of Iowa Department of Computer Science for supporting this interdisciplinary work. That's it.